Hello everyone, my name is Taha Entesari, and in this video I will provide a brief overview of our recent work submitted to ICRA 2023. Our work is titled ReachLipBnB, a branch-and-bound method for reachability analysis of neural autonomous systems using Lipschitz bounds. This work was done with my collaborator Sina Sharifi under the supervision of Professor Fazlyab. Neural networks are being utilized to perform many tasks, and to replace traditional methods, and robotics is not exempt. From tasks such as AI-assisted surgery and autonomous vehicles to simple motion planning, neural networks are being used in robotics. Neural networks can approximate NPCs, and they can be used to replace controllers or to even approximate the whole dynamics of a control system. But this increase in use has not been met with an equal increase in safety guarantees. For a neurally controlled system, can we be sure of the performance of the system? As neural networks are subject to adversarial attacks, can the performance of neural controlled systems be verified under noise and disturbances? Will an autonomous vehicle always correctly detect pedestrians and obstacles and avoid accidents, or will it always have a small but still significant probability of failure? As the use of such neural networks in safety-critical tasks is increasing, the need for providing safety guarantees needs to be met. The analysis of the behavior of these systems is studied under reachability analysis. Reachability analysis is the process of computing the set of all reachable states for a system. Consider a drone that has a possible set of states coming from x0. After a time step has passed, for this system, its states could have evolved to one of possible states in x1. Although x0 was an L-infinity ball, the set x1 is generally a non-convex set. As working with such a non-convex object would be computationally infeasible, it is common to over-approximate it with a new set x1 bar that is easier to represent and work with. For example, the over-approximation could be done by using hyperrectangles. Now, if we were to approximate the reachable set by a hyperrectangle, we would be at a similar situation to the one we started with, meaning that we have a hyperrectangular state set, and we want to find the future reachable sets. Now, suppose that we have a drone with an initial set of states x0, and we want to reach a goal set of goal states. But along the way, there might be obstacles that we want to avoid. Using reachability analysis, we want to find the reachable states at different time steps and ensure that we avoid the obstacles and reach the goal state. Formally, we can write this as the following optimization problem. Maximize Ci transpose f of x for x coming from the set of current states, where Ci denotes the normal direction of a hyperplane. As we are considering hyperrectangles, the Ci would either be EI or negative EI, where EI are the standard basis directions. As neural networks are non-convex functions, this optimization is hard to solve. We propose to use simple Lipschitz continuity arguments to upper bound the optimal value. Let x bar be the center of the input rectangle and y bar be its image. Then if L sub c is the Lipschitz constant of C transpose f of x, we can upper bound this objective by C transpose y bar plus L sub c times the diameter of the input set x. If we do this for several c's, we can find a polytopic over approximation of the actual reachable set. The simplicity of this method lies in the fact that it only requires a knowledge of the Lipschitz constant, the center of the rectangle, and its image. To use this algorithm, we need to address two issues. The first is that these bounds can be too conservative, and the second is the question of how to acquire a Lipschitz constant. To address the former, we propose to use a branch and bound framework. Branching the input space into smaller rectangles allows for a reduction in conservatism. This is because the provided upper bounds depend directly on the diameter of the input set. Using branch and bound allows us to localize the solution of the optimization problem, prune 11 portions of the input space, and find a tighter upper bound. To find the Lipschitz constant, we propose to use a semi-definite program. For simplicity, assume we have a neural network with only a single activation layer. This can be written as W1 phi of W0x plus V0 plus V1, where phi is the nonlinear activation function. Now, if there exists a positive rho and lambda, such that the matrix M is negative semi-definite, then square root of rho is an upper bound on the Lipschitz constant on F. This then yields the following STP to find a Lipschitz constant. We also address the conservatism that can occur to the choice of over approximating set representation, that is, using axis line or hyperrectangles. To address this, we modify our method to allow for the use of rotated hyperrectangles. To do so, we employ principal component analysis to find the axes of maximal variance, and then consider the data in the axes provided by the principal components. This modification does not increase the complexity of our method, as the Lipschitz calculation remains unchanged, and this axis change is equivalent to a linear rotation layer added to the beginning of the neural network. This concludes my talk. Thank you for your time and your attention.